Hi, I'm Brian, one of the engineers at Edmund Optics, and I'm going to discuss the basics of polarization. You have probably seen many examples of using polarizing filters to reduce glare caused by reflective objects. Photography through windows is a great example of this concept. Imagine you are trying to take a picture of a microchip that is protected by a window. The light from the flash reflects off the window and destroys the image. By using a polarizer, we eliminate the glare. In addition to reducing glare, we can use polarizers to show stress in a transparent object, such as a pair of eyeglasses. In order to understand these polarization examples, we need to develop our understanding of polarization. First, we must consider the nature of light as a wave. While light is traveling, it is oscillating. It can oscillate up and down, side to side, or any way in between. Polarization state describes the orientation of the wave's oscillation in relation to the direction of travel. If the propagation and oscillation are in a single plane, we call it linearly polarized light. If the light's orientation changes over time in a helical fashion, we call it circularly polarized light. Linear polarization states are often referred to as S and P. These are references to the plane made by the light wave and the plane of incidence. Rays that are oscillating parallel to this plane are P, and those oscillating perpendicular are S. These originate from the German terms for perpendicular and parallel, senkrecht and parallel. A common mnemonic for remembering the difference is to think P polarized as plunging into the surface and S polarized as skipping off the surface of incidence. Most light sources, like LEDs and incandescent light bulbs, are randomly polarized. You can easily filter a randomly polarized light source to allow only a specified polarization state to pass using a linear polarizer. The light exiting a linear polarizer will be polarized in the direction of the transmission axis. Polarizers can be used in pairs for attenuation. If the transmission of two axes are parallel, the transmission is maximized. If they are perpendicular, commonly called crossed, then transmission is minimized, because we are now effectively filtering out all possible polarization states. By varying the angle between the transmission axes, we can achieve varying levels of attenuation. It is common to specify the ratio of parallel to cross transmission of linear polarizers. This is known as the extinction ratio and is typically normalized. An example specification is an extinction ratio of 10,000 to 1, meaning you have 10,000 times more transmission for P-polarized light than S-polarized light. In addition to extinction, we can measure the performance of a polarizer by characterizing the efficiency. The degree of polarization efficiency is called contrast. This ratio is commonly used when considering low light applications where intensity losses are critical. Several types of polarizers exist today, including dichroic, cube, wire grid, and crystalline. No one polarizer type is ideal for every application. Each has its own unique strengths and weaknesses. Dichroic polarizers transmit a specific polarization state while blocking all others. Typical construction consists of a single coated substrate or a polymer film sandwiched between two glass plates. While you will see high extinction to cost ratios, the construction limits the use for high power lasers or high temperatures. Dichroic polarizers are available in a wide range of forms, ranging from low-cost laminated film to precision high-contrast polarizers. Polarizing cube beam splitters are made by joining two right-angle prisms with a coated hypotenuse. The polarizing coating is typically constructed of alternating layers of high and low index materials that reflect S-polarized light and transmit P. The result is two orthogonal beams in a form that is easy to mount and align. The polarizing coatings can typically withstand high power density. However, the adhesives used to cement the cubes can fail. This failure mode can be eliminated through optically contacting. While we typically see high contrast for transmitted beam, the reflected contrast is usually lower. Wire grid polarizers feature an array of microscopic wires on a glass substrate, which selectively transmits P-polarized light and reflects S-polarized light. Because of the mechanical nature, wire grid polarizers feature a wavelength band that is limited only by the transmission of the substrate, making them ideal for broadband applications. Crystalline polarizers utilize the birefringent properties of the substrate to alter the polarization state of the incoming light. Birefringent materials have slightly different indices of refraction for light polarized in different orientations, causing the different polarization states to travel through the material at different speeds. According to Snell's law, when you change the speed of travel through the glass, you change the angle that the beam exits. This creates a separation in the propagation of the S and P beams. Wollaston polarizers are a type of crystalline polarizer that consists of two birefringent right-angle prisms cemented together such that their optical axes are perpendicular. As light passes through the polarizer, a symmetric deviation between the fast and slow axis rays is created. The resulting beams are of orthogonal linear polarization states and have equal intensity as well as a large angular beam deviation. Users have access to both the fast and slow axis rays, making them ideal for laboratory experiments. In addition, the high damage threshold of crystalline polarizers makes them ideal for laser applications. Now that we have covered the basics, let's return to the original applications. First, we showed how using a linear polarizer reduces glare from a highly reflective surface. Why did this work? By using the linear polarizer, we are controlling the direction of the reflected light we are allowing to pass. This reduces the unwanted reflections and eliminates the glare. Additionally, we showed how we can use a pair of polarizers to see stress in a material, such as a pair of eyeglasses. Why did this work? Stress in a material causes birefringence and will change the polarization state of light as it travels through an object. Since we know that we should effectively block all light between two crossed polarizers, we know that stress in the object has caused the change. There are many other ways to use polarization techniques to your advantage in optical systems. If you are interested in learning more advanced topics in polarization, please continue on to our wave plates and retarders video. If you have any additional questions, our technical support staff is here to help.